Hello students, in this video we'll discuss Cauchy determinants. Let's be given collections of numbers. They can be complex valued. AI, I goes from 1 to n, and BI, I goes from 1 to n. Consider the matrix A, which is formed from 1 over AI plus bj, where I and j go from 1 up to n, provided, of course, that AI plus bj is never equal to 0. Otherwise, we get a problem with this, right? So I want to compute the determinant of A, right? We claim, these are called Cauchy determinants, then the theorem, which is due to Cauchy, states that the determinant of A is the product over I less than j less than n of all the differences of bj minus bi, and then aj minus ai over all possible products I and j go from 1 up to n of ai plus bj, like that, okay? And so, of course, what we want to do is we want to prove this by induction. And so here comes the first step of the proof. So I'm first going to consider the case when n is equal to 2, right? We get something that's non-trivial over here. So when n is equal to 2, we have the following determinant. We have the determinant 1 over a1 plus b1, 1 over a1 plus b2, 1 over a2 plus b1, 1 over a2 plus b2, right? And so, of course, the denominator has the right form. The denominator is going to be a1 plus b1, and then a2 plus b2, and then a1 plus b2, and then a2 plus b1. That's in the denominator, right? When I add like terms. And then what's missing from the off terms are missing from the numerator of the first term, right? So I'm missing a what from the first? I'm missing an a1, b2, a1 plus b2, plus times a2 plus b1, minus, and then I have an a1 plus b1, and then a2 plus b2 from the second terms. Okay, now we just got to simplify this expression over here and figure out what this is equal to, make sure it's of the right form over here, right? So let's look at the terms we have over here. So that I have an a1, a2, a1, a2, those cancel, a b1, b2, b1, b2, those cancel. The only terms that are left are going to be the inner and the outer terms over here. So the outer terms, the inner term, the first terms, and then the last terms are going to cancel in these expressions, right? And so what will happen? So we're just going to get the inner terms and the outer terms over here. So the inner terms are going to be a2, b2, and then the outer terms are going to be a1, b1, and a1, b1. Minus, of course, the inner terms are going to be b1, a2, and the outer terms are going to be a1, b2, right? And so, of course, if I look at these two terms over here, I can factor out a b2. If I factor out b2, I have an a2 minus a1, so that's going to be a b2, and then a2 minus a1. And then I factor out a negative b1, and then I'll have an a2 minus a1, and we exactly have the right form. It's going to be a2 minus a1, and then times b2 minus b1, which exactly has this form over here. So in other words, it's true in the case when n is equal to 2. Great. Now we're going to prove the rest by induction, right? And so what we're going to do is we're going to consider the n by n case and assume the n minus 1 dimensional case. So now by induction, I'm going to subtract the last column. The last column has the form 1 over ai plus bn. That's the last column from every column. Okay. If we do so, what are we going to get? We're going to have a factor of 1 over ai minus bn. That's the last column because the j is the column. Minus 1 over, and we're subtracting the jth column, we have an ai, and then plus bj for the jth column over there. That's the jth column. So I'm I'll do it like this actually. So I want to do this with the plus. I'm subtracting the last column from any column over there. So what we're going to have over here is we're going to have that this is exactly just going to be equal to bn minus bj. Over what? Over ai plus bn. And then what? And then an ai plus bj. Okay? Remember, the j is the column. And so what can I extract? From every column, I can extract this. So extract this factor over here. Extract from every column. And extract this from every row. Hold on. And if I do that, what's the effect on the determinant? So we can factor out, we're going to factor out what? Factor out from this first phase of the determinant by subtracting every column from that. What will we get? We'll have a factor of product of just going to be what? Well, the product I goes from 1 to n minus 1 of bn minus bi from the columns. And then we're going to factor out all of these things from the rows over here, right? So of course we have n rows, so we're going to factor that out. So we're going to have an a bn, and plus ai. So the product from all the rows, I goes from 1 up to n of what? Of ai plus bn. That's exactly the kind of terms we want. Good. And then times, then if we factor this out, then the last column will have all ones in it. Then the last column has all ones. Okay? Because I've extracted this from every row, right? So if I extract that factor from every row, then I have all ones in the last column. Okay? Great. All right, now what we're going to do, now we're going to do the same thing with the row operations, right? And so now, subtract the last row. And what does the last row look like? The last row looks like 1 over, now I have an an, because I'm in the last row now, plus bj. And now what's the role of bj here? Now bj is going between 1 and then what's going to happen at the very, very last row? Well, of course, when j is equal to n, I'm going to have all ones in the last column over there. So when j is equal to n, there's going to be all ones. So I'm only going to consider the case when j goes between 1 and n minus 1, because what's going to happen over there is that the last element, the nn element, is going to be equal to 1. So over here, it's important to realize that the nn element, by doing this procedure, the nn element after this will be equal to 1, right? Okay, and that's going to be very important. So now that's going to give me the induction step over here. So let's do it. So from what does the other rows look like? The other rows look like 1 over ai plus bj minus 1 over an minus bj. And that's going to give me a factor of what? That's going to give me a factor of an minus ai, right? Good, an minus ai, right? Over what? Over, and then I'm going to have an an minus bj. Again, j goes from 1 to n minus 1. Good with it. That's a plus sign actually, right? So it has to be a plus. That's a plus. Okay. That's what we want, right? And then what's left over is going to be what? It's going to be a 1 over ai plus bj. Good. So now what we're going to do. So now I'm going to pull this out of every what? So we're going to take this thing over here, and we're going to extract this from every row. And we're going to extract this from every column. Okay? And if we do that, what are we going to have? We're going to have a whole bunch of factors of what? We're going to have a whole bunch of factors of the product. I goes from 1 up to n minus 1 of bn minus bi, and now I'm going to have an minus ai, because I factored those out of all the rows. And then the denominator, what are we going to have? We're going to have the product. I goes from 1 up to n of ai plus bn. And then I'm going to do an plus bj, but that product only goes up to n minus 1 over here, because that's important now. N minus 1, j goes from 1 up to n minus 1 of an plus bj. And then what's left over is exactly just going to be the determinant 1 over a1 plus b1, 1 over a1 plus bn minus 1, and then a 0 over here, 1 over a2 plus b1, all the way down to 1 over a2 plus bn minus 1 and a 0. And then lastly, I'm going to have a 1 over an plus what? Plus b1, all the way down to 1 over an. Oh, I'm sorry, those are 1s now because I've extracted those, so those become 1 now, excuse me. So those are 1s now because I've pulled those out, right? Those are over here now. That's going to be a 1, and then a 1. Oh, those are all going to be, I've pulled those out, so I get a whole bunch of 1s now. 1, and then a 1 over here, and that was the key important part of this determinant over here, right? And so now what we're going to do is we're going to expand along this last row. So we're going to expand along this last column, expand along this column. And if I expand along this last column, what's left over? All that's going to be left is this subdeterminant over here, right? And that subdeterminant over here, so that last thing is a 1 over an minus 1 plus b1, 1 over an minus 1 plus bn minus 1. And now I can use what? We can use induction here. And by the induction hypothesis, this will bolster up to an n, this will bolster up to an n over here, and we'll get exactly the correct formula that we want, that namely that this is the Cauchy determinant. So by using this formula in induction, and by carefully extracting from the rows and columns the exact terms that we need, we see we get this representation for the Cauchy determinant. So the Cauchy determinant comes from induction in 2 important steps, by subtracting the last column from all of the previous columns, and then subtracting the last row from all of the previous rows, and then that puts everything into the same form by these rational expression ideas over here. And so I don't have enough space to actually write down all these determinants at each step, but follow these 2 steps in sequence and write out these subdeterminants to make sure I understand the sort of the structure of what I'm pulling out over here, to make sure that once we have these terms over here, these exact terms in my structure, I get this exact formulation of the determinants of a Cauchy matrix. Thank you very much.